Okay, this is the review for the second midterm. The second midterm occurs in week 9. Exactly the same details as the previous ones in week 4, was it? I think it was. Closed book, closed notes. You get scratch paper, which is really the back of the equation sheet, which you see below and will be given to you by the TAs. Bring a calculator, no smartphones, tablets, or calculators that have extra information on them, etc. Especially no communications. I don't know if those exist or not. And it's on Monday, Wednesday, and Friday of that week, 8 to 8:30 in class, typically opening up a bit earlier. The material covered is the stuff between weeks 3 and 7, so it covers force on structures, it covers Bernoulli in weeks 4 and 5, it covers conservation of mass and conservation of momentum. And so the individual components are, on Monday is chapter 3 essentially, forces on structures and mechanisms by which things fail or rotate. The Wednesday one is Bernoulli, essentially things that we covered in week 5, not rotational Bernoulli, but just linear Bernoulli. And on the Friday, conservation of momentum, which is also actually conservation of linear momentum, not rotational momentum. So you can decide based on those what you should look at. So I'll go through the main things that might turn up on the test. You can see from previous review sessions whether I've been leading you astray or giving you the real deal. There is a question on force on structures. You know that we can get forces on structures as a resultant, which is just the product of the unit weight times the depth of the centroid, which gives you basically an average pressure multiplied by the area over which that average pressure acts to give a total force. It's important to note that although you calculate the force from the location, the depth below surface of the centroid, which is the balance point of the shape, if you like, if you held it up on your finger, the force acts at the center of pressure. And the center of pressure is given by this slope distance y sub r. We can always calculate y sub r as the slope distance in the plane as you go down from the surface, some distance to the centroid, which is yc, and then a distance delta yc as you go from there, which should actually be this magnitude here, right? So the depth below the centroid of the point of action is delta yc. You can always get this magnitude just from this equation here. This is the slope distance of the centroid, which is this point here, the balance point of the plane. And the distance below that, delta yc, is this term here. This is delta yc. It's given by the second moment of area about the centroid divided by the depth of the centroid, slope distance of the centroid from the surface, multiplied by the area of the plate. And so there's some standard results that give you that. The second moment of area is b a cubed over 12 for a rectangular plate. It's pi r4 over 4 for a circle, and it's ba cubed over 36 for a triangular shape. The depth of the centroids of each of these is, the center of balance would be half a. It would be the center of the circle, and it would be a height one third the height down from the base for the case of a triangle. So these are the individual areas. Area of a rectangle you should know, triangle you should know, and a circle and a triangle you should know, but these are standard results. A is always the distance in the depth that pressure is increasing. B is the distance which is parallel to the surface. Some standard results in terms of behaviors. Certainly the resultant acts at 2/3 of the height down if it intersects a free surface. If the pressures acting are uniform, say as due to a gas, then the distribution of pressures is not triangular, but it's just a prism, and it's just equal to the mid-height depth of the centroid times the unit weight, which is the height, or the average pressure multiplied by the area. So the average pressure for a uniform distribution for a gas would just be a uniform distribution here, which would be an average pressure. And if you multiply that average pressure by the area, you get the total resultant force. And that total resultant for that would act at the half height. This would be h over 2. So, okay, so we've seen that. So we know also that although we can resolve around any point to get moments such as this, so if we wanted to rationalize, actually you don't need this, so I actually won't go through it in much detail. We don't really need to know this. But if you wanted to, and you know what the prismatic distribution was if you're below the surface, and you know the triangular distribution, you could take a moment about any location and resolve the point at which the resultant was acting just by using this equation. You know where the magnitude of the force for the prismatic distribution, you know that it acts at half height along its depth. You know the magnitude of the force for the triangular distribution. You know that it acts 2/3 of the way down its height. If you take these moments around, say, this point, or this point if you want to, but in here we're using this point, you know that the total force is equal to the sum of the prismatic and the triangular, and so the only unknown is the location of the point of action. So you can get that from that. So that gives you the location where the resultant acts. But if you're looking at a particular failure mode, then you need to resolve forces around that particular failure mode. So for a rotating dam, a dam rotating about its toe, it would be a failure mode that would allow this domino to fall. For the gate that we covered in class, which is on a hinge, you have to do it around the hinge to be able to get that magnitude, this case here. So those are the cases for forces on structures. On Wednesday, it's Bernoulli. You know that Bernoulli is pressure, elevation, and velocity heads written between upstream and downstream. Hopefully you know 5 of these and you can solve for the remaining 1. The magnitudes of upstream and downstream potentials, if you like, are equal, so you can write them equivalent to each other. If you have 2 unknowns, then you can actually link the upstream velocities and downstream velocities by continuity, just saying that the mass rate into the streamline is equal to the mass rate out of the streamline, and by doing that you can link the magnitudes of the upstream and downstream velocities. And so upstream, downstream velocities are linked, then you reduce your 2 unknowns to a single unknown. We explain Bernoulli behavior in terms of, say, flow in a pipe. The elevation, pressure, and velocity heads represent the individual heights on this. For Bernoulli, where there's no head losses in the system, the energy grade line is horizontal and has to be the sum of elevation, pressure, and velocity heads upstream and the same downstream. They might change. We talked about if you had a pipe that went upwards, then the magnitudes of the pressure in this pipe have to change to compensate for the fact that you're elevating the z-coordinate of this point. The velocity, if it's a constant area pipe, has to be the same as it travels through here. So the velocity head has to be the same. And so what gives is that the pressure must be reduced to accommodate that. And so we understand that. We talked about static and moving coordinate systems. The fire department of New York was the velocity of the control surface is moving at some velocity. It's squirting water out at some velocity w. And so to a static observer, that bead of water at the tip of this is traveling at a static velocity. If you sum these 2 vectors to equal 1 vector, then this is the relation that links them. We know that along a streamline we can write between upstream and downstream, and we have to know velocities, pressures, or elevations to be able to deal with that. If we need to link upstream and downstream velocities through their areas, we can use the continuity equation. We know if we apply Bernoulli for a free jet in a big tank with 0 velocity on the top and atmospheric pressure, we know that the standard result is just that the velocity is 2 times gravity times the elevation change between that point relative to the free surface. It doesn't matter if it's squirting out of the bottom vertically or out of the side horizontally or at an angle, it'll still be the same velocity as we get from Bernoulli. We know that if it's inclined, then it's actually a streamlined velocity that we calculate. So this is a streamlined velocity. And so if we want to calculate the magnitudes of the x and z velocities, we can merely take the vector components of those as cosine theta and sine theta to represent those. We know that from Newton's law that a bead of water traveling at some velocity vx without any forces acting on it will keep on traveling at vx. We know that a bead of velocity traveling with its component in the vertical direction, vz, will slowly slow down until it becomes zero vertical velocity. And when that vertical velocity is equal to zero, that is the peak of its arc. But at the peak of its arc, it will still have the same horizontal velocity that it had when it came out of the jet. And so this would be the same. The horizontal velocity would be the streamlined velocity at this peak of its arc. We can use your statics equations or dynamics equations to get how far a bead falls in a matter of time if we know its initial elevation, if we know its initial velocity, and the acceleration due to gravity. And we know how far the velocity of something is equal to its initial velocity plus the acceleration times time, if there's an acceleration. So we can also use velocity is equal to length over time, and clearly from that the length traveled in a given time is just going to be the product of velocity times time. So we can use those individual expressions to look at our understanding of the flow of fluids, in viscid fluids. There are no manometer questions in the test. We talked about conservation of mass. There's not really a question on that per se, but it serves to make the concepts that mass rate out of the system has to be equal to the accumulation by a change in volume at constant density or a change in density at constant volume. This is the idea of a tire being filled. This is the idea of a tank being filled. We need to be mindful of the sign conventions where the mass rates are positive if coming out of the control volume and negative if going into the control volume, because the arguments about the dot products and the directions of the unit normals in this. And the sign convention, in addition to mass flow rates being positive outwards, are that changes in density or changes in volume are positive if they're increasing. Conservation of linear momentum is really just a manifestation of Newton's second law. F equals ma, which we prefer to write in this as d mv dt in terms of our substantial derivative. If we do that, we can use Reynolds transport theorem to write the vector of forces equals mass times acceleration. That's all this is. Mass rate times a velocity. Mass rate is a mass times a mass rate times a velocity. So this is the acceleration. This is the momentum term that exists there. We have to remember that both the velocity and the force terms are vectors. They have x, y, and z coordinates. Their summations individually of these components. Typically, we'll look at resolving one component at a time, say behavior in the x direction. We have to be mindful of the coordinate system again. Velocities and forces are all positive in the x and z directions, the Cartesian directions. Certainly the velocities that we use here are, and the forces that we use here are. But the mass flow rates follow the convention of conservation of mass. Mass flow rate is positive if it's coming out through the system. This is a positive mass flow rate. This is a negative mass flow rate. So this is velocities in resolved. This is a velocity in the z direction. This would be positive vz. This would be positive vx because of the coordinate directions. We did some examples with static and steady systems. Static system means that the velocity of the control surface is 0. A steady system is where the sum of the mass flow rates into and out of the system, in this case on the left side and the top side, those mass flow rates would balance. So velocity in and velocity out would be the same. So these would be W's if in that particular case. And so if that's the case, that it's static and steady, we can simplify this relationship that the forces acting and the mass flow rates acting are pre-multiplied by the velocity relative to the control volume. So W is the velocity relative to the control volume. In other words, for our fire department of New York system, this was the velocity coming out of the hose. So it'd be the velocity coming out of the sled in this particular case, or going into the sled. And of course the mass flow rate is just equal to the area times the velocity, which is a volume per unit time, multiplied by a density, which is a mass per unit volume. So that comes out to be kilograms per second. The only tricky one, which you actually don't have to deal with, I'll tell you right now this time, is that if it's unsteady, then you can't use this on its own because, say, the gas canister. It's unsteady because it's losing volume, and that volume isn't being replenished in terms of the cylinder. And so we can't use this expression, but we have to accommodate the fact that the control surface is moving. As I said, that's not on the test. And this also is a curiosity, that to be able to do work or to convert power, you have to have both a force, but it has to be moving through a velocity. If you have a force that isn't moving, then you have no power. Or if you have no force that is moving, then you also have no power. And so we have to look at the fact that both the force and the control surface is moving to make energy in our system. And the example we gave, if you have no velocity but a force, a maximum force, then you have no power. If you have a maximum velocity but no force, you also don't have power. Somewhere in the middle is the Goldilocks zone where you have both. And I guess the other thing to mention in the case of these sled examples or vane examples, if you allow the system to move with no force acting against it, so if the force is equal to 0, then the control surface volume will be a maximum, and it will be the velocity of the impinging fluid if it's coming in horizontally. And in the opposite case, when this is equal to 0, is not equal to 0, then when the force is large enough to stop the velocity of this, so it's a static sled, in other words, it's 0 velocity, then the force in that particular case will be maximum. So those are the two end member conditions that you can look at. So that is about it, I think. I think everything's on here that you need for the test. And this will be the equation sheet that you'll be given physically in your hand on the day, the back of which can be scratch paper for you to use also. Okay?